Okay, thanks for coming. So we are from AI Training Platform at LinkedIn, and yeah, today we are glad to share our recent work about how do we use Ray to scale our online training solution at LinkedIn. Yeah, so first of all, what is online training? So compared with traditional model training, which was trained on batch-based offline data, so online training system is a continuous feedback loop between user interaction data and model itself. So basically every click, every new job post, every interaction between becomes part of a nearline training process. So at LinkedIn, we have onboarded our system to major AI use cases, including incremental training for feed and ads, or online training for jobs you might be interested in. So why do we do online training? So because basically it can bring us benefits from both business and infra point of view. As we can see in the right-hand side, so the model update frequency can be reduced to 15 minutes compared with the daily incremental training and the quarterly cold start training. The fresher model can also improve the online model performance. So we are seeing more than 2% improvement in job application rate when we switch to online training for job recommendation models. So furthermore, it can also reduce the computation costs when we want to frequently retrain a model with large time window. As we can see in the slides, so instead of doing daily retraining, so we can avoid training on previous trained data, and also we were able to enlarge our time window by training based on previous checkpoints. Okay, and here is how we are building the online training platform. So our system is built on top of our internal Kubernetes computing infra, and each training job will be launched as a Ray cluster managed by our flight-based workflow management. In application layer, we have decoupled the data workers and the training workers served as reactors. So the data workers are implemented in different ways to take either offline data managed by Iceberg or streaming data managed and stored in Kafka. So the training workers are implemented in either TensorFlow or PyTorch to run the standard training loop, so which we will mention later. And we are also using HDFS to store the model checkpoints and training status. After the training is finished, we just export the model and do the required post-processing and then publish the model for serving. So also I want to mention, when we are implementing this system, we also met some challenges. First of all, we want to generate the training data where feature is consistent among training and inference. So this is a very big transition because before online training, all of the features are loaded offline, where the feature might have drifted since the user action take place. Yeah. And secondly, we have an in-house Kafka Python client, which is based on REST proxy. So this is not as performant as the native Java implementation. And also, we also need to deal with the fragile runtime environment. So basically, this means before incremental and online training, so AI engineers train their models in their own custom Python image and their custom training scripts, so which makes dependency management very difficult. So every time an issue is happening, it becomes very hard to go into user's dependency chain to isolate infra code and user code and find out the bug. But in online training case, the issue resolution timeline is usually very short, and we also need to guarantee that the runtime environment can be updated and roll out timely. Yeah. Furthermore, in order to make our system fault tolerant enough, we need to be able to take snapshots and recover from previous failed states. And finally, we also need to capture the anomaly early and send timely alerts to customers with proper monitoring tool. So in the next, I will hand over to my colleague Yang to deep dive into how do we resolve the consistent training data generation part.
Thanks, Chen, for the overall introduction. Next, we will go to our first engineering challenge, where how we generate consistent training data between for training and inference. So this is what we call streaming training data generation. Although this is a Ray summit, but we will introduce something that's not directly built on top of Ray. Overall, here is the graph of overall our system is basically a typical stream processing project where from the the data flow from left to right, where like we have the several Kafka topic as input and go through several like stream processors, and then like send the joined like samples into a certain Kafka topic, and then consumed by another like service to do certain additional transformations, and eventually like this data is written into destination Kafka topic, and then like going to some like different sync such as HDFS or like going to the online reading for the online training. So let's maybe dive deeper into this high-level system. Yeah, so basically the first part is basically what we call like the attribution service. So in this service, like its input is several like Kafka topic, and this Kafka topic includes the feature tracking, where like actually the feature is being logged through your online like maybe model inference like service, and to like record exactly the feature value that you use for inference. This is one very important thing for you to achieve consistency between training and inference. Yeah. And besides this like feature tracking topic, there is also some additional topics such as like jobs apply or like jobs click, these kind of like signals from the user. This is usually like certain signals that is baked into like some vertical teams like backend service, and like basically they are like receiving this signal from users and send it to this like Kafka topic for downstream to consume. So there is like a stream processor where like we do the feature and label or like user signal joining based on certain like IDs. In this case, it could be some impression IDs that we can uniquely identify like for this particular feature value, which impression or click events from user we should join with. In our setup, we use a 1 hour like window joining. This gives us the maximize like the positive labels that we can receive, with a balance on like how much like things we need to store on this like joining like stream processor. But still like this 1 hour joining is pretty large. So we did an optimization here that we are going to offloading the feature vectors into a KB cache. And when like to reduce like the memory pressure on the stream processor, and when the event window fails, so basically we have one additional step which we rehydrate these like events that after like the impressions or like and the labels is joined, we join also using the same like impression IDs to fetch like the feature values and join it together. That give us the eventual like kind of like feature like some like training samples, and then we write it to one like Kafka topic. And the next part is what we call like data transformation service. So this is also another like stream processing component. And here, like what we do is that we do certain like transformations on the features. Basically, like there is like certain format that is optimized for the feature tracking, which is kind of like in a nested format. So in here, like we are going to flatten it into like kind of like something like a white column like format, which is optimized for like training. So that like your training like data ingestion or reading can effectively select the columns that you want to use for training. And besides that, we also have some like different kind of pipeline configurations in this stage, so that you can certify something differently. For example, how you want to like downsampling your negative samples, and also how exactly your labeling logic should be. So basically, in the original event is only have the raw user events. You can apply different kind of labeling logic so that you prepare different set of training data for your model. And also like you can specify like different sync source. For example, like for certain Kafka topic, we are going to ETL it into HDFS, and this like ETL the data going to be used for offline training. This is like one like way that how we achieve like the training and the inference time like consistency, because like feature value is logged during inference and it is used for training, which is the exact same like version. Instead of that, you need to do the offline joining, like using certain Spark pipeline to do offline joining, where you need to version your feature correctly so that you can do the right time like point of time joining. And besides that, you can also simplify for like this is for online training. So that's like I'm going to like pass to my colleague Tao, who will introduce how we build the data ingestion for online training on top of RAID.
Okay. Thank you, Yang and Chen, for setting up a nice stage. So now we have the nearline data prepared. The next stage is going to fed that data into our trainer. So I will briefly talk about what kind of problem we encountered and how they help us resolve those issues. And so the long story in short is our Kafka infra was mainly built for the Java stack. However, like most of our machine learning engineers, our model was trained in Python. So the challenge here is that we have to move the message across a language barrier and fed into the model, need to batch them, preprocess them, turn them into the tensor that the model is able to consume. And what makes things even worse is that our legacy messaging API allowing us to do this transformation has two major issues. One is actually making the blocking call to fetch the message from our Kafka cluster. Then two is it's only single-threaded. So Ray actually helped us resolve this problem in a very elegant way. So thanks to its first-class citizen support for the Python native authoring developing experience, we're actually able to use Ray call to simply build a data injection service that is scalable and robust. And the solution is also very straightforward. We just ask one Ray worker to handle one request. But all those things pretty straightforward and simple. This solution actually scales very well. So it's shown in the figure on the screen. You can see our data injection service throughput actually scale almost nearly from 1 CPU up to 100 CPUs, 100 workers. Okay, and then we also try to do some optimization to minimize the data transport between data transport costs between the different workers by leveraging the Ray's objects.zero copy. So basically, our Ray actor, if we ask the Ray actor to simply return a dictionary or the raw message, it's actually 5 times slower if we let the actor return a NumPy array or a TensorFlow tensors. This is mainly because that we actually pay additional serialization, deserialization, and copying if the data is not the native NumPy array object. So that actually really helps us further improve our throughput. And another thing I want to mention here is one of the issues we encountered before is that our Kafka messaging API is blocking. And we're actually able to use the Ray's data generator pattern to implement some prefetch mechanism. So the way how we do it is that we're actually able to allocate some workers to do the I/O in prefetching. And this I/O stage is actually able to overlap with another pool of workers that is handling all the heavy lifting on the data preprocessing, parsing, batching, and tensor filing. And this overlapping actually works very well and further give us another 2 times improvement in our throughput. So next, I'm going to turn the mic back to Chen to dive a little bit deeper into our online training.
Okay, thanks, Tao. Let's take deeper look into the training side as well. So as we mentioned before, so managing a Python environment is a big headache for us. So instead of letting user build and manage their own environment, we ask user to call our Explorer API to compile and serialize the training compute graph, including forward, loss calculation, matrix backward, and optimizer updates. So internally, we are using TF saved model and torch export to save TF function or torch fx graph. The static graph also simplifies the reproducibility and safety, so we can version and validate the compute graph much easier than validating Python scripts. So besides training compute graph, we also take the snapshot of other internal training status, including model parameters, optimized states, data loading states. So specifically for offline incremental training, we store the date partition managed by Iceberg table. For online training, we keep the Kafka offsets and internal timestamps. All of the artifacts are packaged into the folder and stored in HDFS for record keeping. Let's also take a deeper look into the layout of the actual training execution. So we launched different reactors for different roles. So we call them as service. During the training runtime, we no longer need users shipped Python code. All we need are the serialized model artifacts and the input datasets. And standard training loop, including forward, loss, backward, and optimizer, will be executed. So our system supports distributed training using Harvard for TensorFlow and Torch distributed built on Ray train. So one thing to mention is that for online training use case, our QPS for training data is not large enough for distributed training. So while for offline replay experiments, we usually have batch data which requires distributed training and evaluation. In these cases, we can also launch evaluation service which can take multiple checkpoints saved during training and run evaluation on same evaluation datasets in parallel. And also the matrix calculated during training or evaluation will also be sent to our centralized monitoring and alerting platform. So here are some common alerts we have set up. For example, the input traffic monitors the QPS of training data, and we can also look into how much offsets we have been lagging behind. And label distribution is used to monitor whether the sampling rates are correct. And we also have matrix set up for real-time progressive evaluation matrix. Yeah, and so far above is all of our existing implementation, and then I also want to quickly share our ongoing and future works. So first of all, we have explored ways to run streaming partial parameter updates. So instead of going through the entire model publishing and deployment cycles, we send the updated parameter from optimizer directly to the serving container. And for some parameters like embedding tables, we might also have sparse gradient, which causes sparse embedding updates. So we can also just send the updated rows to save the traffic of syncing the entire embedding table. And also our benchmark shows that the model updates latency can be reduced by 15x if we apply this approach. Yeah, we are also exploring how we are doing incremental and online training for sequential model. So compare with the regular point-wise style training. So the training dataset looks different. So it's usually like users' past action histories instead of the activity partitioned by days. So we need to figure out ways on how to keep track of the updated user activities and to avoid retraining on past sequences. Also, after we take the training artifacts, we want to save the AI engineers' efforts to tuning the number of GPUs and I/O configuration. So we plan to run some graph optimization paths to run further compilation, kernel fusion, or replacement. We're also exploring having some hardware planner which can automatically decide what is the best hardware requirement for this job based on the user-provided batch size before we start the actual training job. And finally, we are exploring some like ARM-based recommendation in LinkedIn as well. So where there are also not only training, but also like post-training steps, including the model distillation and the reinforcement learning. So we are trying to extend our system to support more types of actor service based on array, like teacher inference worker, student training workers, or like RIR reference workers, actors. So these kind of different type of worker can communicate with each other via message queue, and also we can explore some RDMA feature recently launched in RAID directly transport. Yeah, and I also want to take a moment to thank our training and platform team and our AI partners in Talent Markspace team for their collaboration and support. So this project is a true cross-functional efforts bringing together infra and ML experts. Yeah, and thank you for your attention. I'm happy to take any questions.
Daily or maybe weekly review of this trained model, like sign off by MLE, or it's fully automated and we, like MLE only evolving into this like quarterly retraining? Basically, like, do you have any human in the loop before you release, or like at least like in a short period?
Cool. Yeah. Cool. So the question is about like how whether we have any human in the loop to review the quarterly published trained models. Or weekly, okay, yeah. So basically we have a online A/B testing system. Basically, users train so in the regular world, like they just train their CoSAR models and publish it and compare it with the original like CoSAR model. And we have platform to visualize, okay, based on this model, what is performance compared to the baseline model. Yeah, and these two models are trained in the same time window. And for incremental training, we also have like so they have daily retrained model and publish to these two slots, and we compare them like with same time window. Yeah. Okay, so the question is about how do we, how do we validate the quality of the model? Yes, so basically, this is purely based on like whether this model is performing as good as the baseline model. For example, if we want to compare the incremental training or on training model with the baseline, we just have a co-star model that is fixed without updating. And we have another model slot which is published daily or like published every 15 minutes. Then we can compare this model's metrics with the baseline model. If it looks better, for example, we see the job application rate is being higher, then we say this is a better results. What is frequency of updating? Yeah, it's depending on verticals. So for example, for ads, we maybe have like a per 12 hours publishing, or for feed, maybe we are doing daily incremental training. So this is based on like each of the use case and their experimental results on which is the best frequency to publish the model.
With separate evaluation dataset services and training dataset services, how do you ensure like there's no data leakage? Is there like a predefined robot set?
You mean the question is about like how do we ensure there is no leakage of the
Label leakage with two separate like evaluation dataset service and a training dataset service.
Oh, I see. Yeah, this is a good question. So, so basically for online training, we don't actually have any evaluation test because this is real-time training. So we do progressive evaluation. So this is like we evaluate the AUC on the fly. But for incremental training, like we usually use a past time window. And we also keep a more recent time window as the evaluation dataset so that each of this dataset is partitioned on dates so that we don't train on the later data. We just train on previous data, just purely for validation purpose. Okay. Yes.
So you said you use the torch for expert for all the models. I wonder, did you see any like compiled failure?
Oh yeah. So the question is about like whether we are seeing any compilation error when we're doing torch export. Yeah, so this is also a good question. So we are currently in the transition state between TensorFlow and PyTorch. So when we use torch export, we notice several issues. So also like, for example, we cannot see any kind of graph breaks, and we can also control any dynamic shapes. So we need to set up these kind of, during export, we need to set up these constraints. Like, okay, so this is the constraint for the current export. So you cannot write model like this in order to export this model. So yeah, so that is currently what we're doing right now.
So if you see like compiled failure, you will still use TensorFlow?
Yeah, so if we see compilation error, usually like we just tell what to change the model. So usually so currently we have not seen such like issue that cannot be resolved by torch export. But yeah, in the future, if we see this kind of issue, we might need to resolve with open source PyTorch team. Okay.
So do you do any testing on every single new model? If that's the case, how long you can conclude the experiment?
Oh, so the question is about how do we...
So basically, my question is whether you do A/B testing on every single incremental training model or just like a full training model. And
Yeah.
also, the next question is how long will it take to conclude the experiment?
Okay, yeah. The question is about how long it usually take to validate this model is better, like if we are keep doing incremental training. So, so it also depends on different vertical. For example, for jobs recommendation, they use like 2 weeks to validate. Okay, this model is good enough. Then like we can say this is a better model than previous. So it's purely based on like the data set volume and what is the traffic volume. And we need to make sure the A/B testing is better. Then we need to statistically make sure this is better. Okay. Oh, sure.
Yeah, so if you do like A/B testing, you will conclude in 2 weeks. So how do we but you do for example training every 15 minutes? How do you pick a version to push to production to A/B test?
The question is about how do we keep the version
So
in?
you have so many versions, right?
Yep.
Every 15 minutes, but the A/B testing you can conclude like in 2 weeks, right? So you cannot have so many versions in production. So I'm curious, like which version you pick to push to production and do A/B testing.
Yeah. So the question is about how do we? So which version is used to like keep record of when we are validating these like 14 days time window. Yeah, so actually, so basically when we publish a new model, a new version is generated, and it will overwrite the previous version. So for this specific model slots, we only have one version, which is the latest version. Yeah, so basically we compare this with the static model in other slots. Yeah.
Yeah. And also, like, I want to add one thing on that. Basically, like, it also depends on what is the hypothesis you are testing, whether you are just trying to compare whether the new model itself, like your you train from CoStar training, and compare with the production model whether it's good, or you want to just verifying like whether the enable of the online training is good or not. So basically, those are like different hypotheses. So regarding like that would affect how you set up your experiment and decide like which version you should launch. Yeah.
Do you have a primary server internally for the inference? Because it looks like you can update the weights by
Yeah, so the question is about whether we have parameter server for distributed training. So yeah, this is a good question. Basically, previously during the design stage, we prefer to use a parameter server instead of like a all reduced based distributed training. Yeah, but the reality is that we currently are not seeing any need for online training in distributed way, because our QPS for training data is not that high. So basically, the throughput is our trainer can totally take the 1,000 throughput so we don't currently we're not doing any parameter server based distributed training. But in the future, if we are training larger model, then we can consider this when we are having larger traffic. Yep. Okay.
What are you using for serving?
Yeah, the question is what are we using for serving? So for serving stack, we have our internal Kubernetes-based serving stack, like not on array based on a native Kubernetes cluster, and that using like Java and plus some like TensorFlow serving or like Torch native serving. Yeah. Yeah, I think most of the benefits are coming from data loading side. Maybe Tao can talk more about it.
Yeah, so I think Ray just really help us manage the different states on also decouple the logic between the training and the data injection, and also make our data injection more scalable without really redesign our whole Kafka Java-based stack.
So your Kafka is our legacy thing?
Yeah. Yes. Basically, our client is too slow, but the rate really help us need scale it up.
Yeah, but you could have chosen the Scala and Databricks side, right?
Sorry, what's the question again?
You could have chosen the Scala on the Databricks side.
The Scala and Databricks side? That's something I'm not super familiar with. Maybe we can talk about this offline. Yes.
Okay, sounds good. Thanks for coming. Yeah.